But do you see my screen, guys?
Yes.
Wonderful. Okay, so if remember in last week uh, we discussed specifically on energy efficiency of the process, how we can improve process um, heat exchange in general. As we discussed here in any process, including biorefineries, we have two types of heat exchangers. We have process-to-process heat exchangers, like shell and tubes, for example, and utility-to-process heat exchangers, like boilers, condensers, whatever. As we discussed, when we are using a utility heat exchanger, we are dealing with electricity, steam, and water. Okay. So when we talk about energy efficiency, as we discussed last time, our uh, our plan is to make sure our plan is to make sure uh, we have maximum uh, overlap between process streams. So we have maximum process to process heat exchangers and minimum uh, usage of utility. So we want to have minimum cooling and minimum heating by cooling water, steam, and whatever. That's why we said, okay, we have to do optimization to find the minimum temperature difference in the network of heat exchangers that we call it delta T mean, and then we move on. But on the other hand, when we talk about a heat exchanger network, okay, uh, we should not put our focus only on process-to-process heat exchangers. We have utilities. So in utility, we have steam. So we have to generate the steam in our boilers, and also we have a lot of water streams. That's why last week after thermal pinch analysis, we discussed about water because you have some unit operations that demands water, and some unit operations like filters, for example, that provide water, they supply water. Okay, so we have also sink and source of water, and therefore we need to also optimize water consumption in the whole process, and then let's see what is the if let's see if we can gain some water for utility. Okay, that's why, as presented in overall in this diagram, you have always the main process, and beside the main process, you have the utility system. And if you want to have an overall uh, optimized process in terms of energy efficiency, you need to, you need to consider that uh, you have to optimize energy efficiency not only in the process itself, but also inside the utility system. Because in the utility system, for example, you have a network of water back and forth between the main process. So you have to optimize even the water network in the utility system. In steam generation parts of the utility, you have several boilers, for example. For example, fluidized bed combustors or pulverized coal combustors, whatever. So you have to also optimize that heat network in the utility system. At the end, you will end up with the uh, overall process that is perfectly energy efficient. So From another point of view, if you want to summarize this kind of overall process integration in terms of especially energy efficiency, so we are, in the overall, when I say overall, I mean the main process, chemical process, biorefining process, and utility system. The utility system is not just steam and water. I just want to emphasize it again. Generation of steam, generation of cool water itself is another factory. Utility is another factory. If you go to a refinery, you see that utility uh, department itself is a large factory. There are a lot of process equipment in the just utility system. So it's not just there is the tap water. You just open the tap water from the city and then direct the water to process, or just put a kettle and boiler and just evaporate water, make steam. It's not like that. It's a complex system itself, the utility system. So in overall, if you look at the process, overall process, when I say overall process, I mean biorefinery and utility. You have different sections. You have internal heat recovery sections that mainly means, for example, process-to-process heat exchangers, okay, that you have to optimize. For example, by pinch analysis. In the water network, you have water streams, from different concentration or purities and different temperatures. Something that we need to consider is that we should not mix the water from different temperatures in a very inefficient way. You have to be careful. Water reutilization. We need to apply a water pinch method to optimize water consumption. Okay, in the process, you have condensates. You have to think about condensate recovery. You have energy conversion. Part of the steam that it generates in the process, you can use it for turbine, for example, produce electricity. Energy upgrading, as we discussed, we are going to discuss later today. Sometimes in part of the process, you have some warm areas, for example, or some warm streams, but those streams are not hot enough to take advantage of that energy in a heat exchanger, because the heat exchanger can be expensive. But since anyway, there is a source of energy even at let's say, for example, at just 40 degrees C, 40 Celsius. You can take advantage of that energy, so you can take the heat of that kind of warm temperature, but use that energy at a much higher temperature somewhere in the process. This is called, we are going to discuss it, this kind of energy upgrade is done by something that is called heat pump. I don't know if you have seen at homes, here in Canada especially, usually houses, they have a heat pump. So they get the heat from a quite a low temperature, and then they transfer the heat and release it at a higher temperature. It's a kind of heat integration that at houses. In Canada is very common. So there is a systematic um, approach that I want to propose here, that you can take in order to study how you can improve energy efficiency in your process, and then uh, study and then apply some uh, uh, projects or some solutions to improve uh, energy efficiency of the process. So there are different steps. Step one is just a data gathering in order to do kind of process simulation. So first step that you have to do, you do a process simulation. So as we discussed last time, process simulation is a very interesting tool because if once you do process simulation, you can apply some evaluations, like for example benchmarking. So benchmarking is the process of comparison a simulation data with the actual data. By comparison of the actual data that you collect from the plant with simulation data, you can identify uh, if first of all if the process works properly, if there are some issues, many different information that you can get from simulation. So this kind of benchmarking is not only for comparison of your process of the simulation with your own plant. You can use the simulation and do benchmarking with other plants. I mean similar plants in other companies or other countries, as long as they are published and available. So by this kind of benchmarking, at the end you can identify um, um, a kind of a characteristic of your plan of your process. Of course, what something else that you can do is to apply thermal pinch analysis. Once you do simulation, you identify heat sink and heat source of the process, okay, and you identify that okay, I did my this simulation. Now I noticed that the plant that is running now it has a lot of heat source and heat sink, and maybe by applying a thermal pinch, we can really minimize utility consumption and improve the process heat integration. Okay, and after, by the way, after these all these evaluations, process evaluations, another step that you have to do, and is quite something interesting, is called equipment performance analysis. Why equipment performance analysis? This is something interesting. You know, when you design, let's say you do process simulation and then you apply, um I mean, you apply kind of improvement in your process. You apply something in terms of improvement. The problem is that always when you apply any improvement to process, you always assume that for example, piece of equipment that you just put in the process is going to work perfectly. For example, you did simulation and you notice that a kind of a specific valve has to put in one specific string. You just want to just to put a valve, okay, for any reason. We don't care about the reason. But the valve itself, after some time, could undergo kind of corrosion because of the flow that passes through the valve. So the valve doesn't work perfectly. So when you close the valve, there is still some leakage from the valve. So the valve doesn't perform perfectly. In other words, you assume in the when you simulate or and then when you apply kind of improvement, always you assume that the process, the equipment is going to work perfectly. But as a matter of the fact, the valve, for example, undergoes kind of aging, is old, doesn't seal when you close it. So uh, it doesn't perform very well. If you put a new heat exchanger in the system, you know that from heat exchanger heat transfer course, I guess you remember that there is a problem in heat exchangers that is called fouling. So when the fouling starts to grow inside the heat exchangers, you know the heat transfer coefficient is going to deteriorate. So you don't have the good heat exchange as good as a new heat exchanger. That's why we usually define key performance indicators (KPI) for each piece of unit operation in the process. Okay, and always we have to integrate also these KPIs to uh, we have to integrate these KPIs into our energy efficiency analysis in order to identify that okay, I did thermal pinch, apparently everything should work, but after some time, does the heat exchanger do the right thing, the right heat exchange that I expect or not? So anyway, after simulation, after benchmarking, after identification of KPIs, key performance indicators, now you can start to really think about uh, kind of integrated or simultaneous energy and water analysis. As we discussed before, you apply thermal pinch and water pinch to identify first heat sink and heat source or water sink and water source of the process, and then you start to make strategies how they can look like. And after that, in step 5, you start to design your heat exchanger network. But but in step 5, when we design heat exchanger network, again, remember that this kind of heat exchanger network is always supported by, I mean, it has to be supported by water pinch analysis and key performance indicators. So that your heat exchanger design could be kind of robust. So you always identify that, for example, um, these number of process-to-process heat exchanger that I have designed at a certain point are not perfect. So maybe you need to consider kind of bypass or kind of supplementary or backup heat exchangers. So these are things that in order to make your process um, robust, so that or you can prevent inefficiency in the process. After you design your heat exchangers, this overall heat exchanger design, of course, you have to do another post benchmarking, and specifically you have to design kind of techno economy approach to make sure that all those uh, uh, new improvements that you are going to apply to process is going to be not only technical but also economically promising and viable. So these are 6 steps. If you follow, you can make sure that now you have a process that is really energy efficient. But these 6 steps that I just mentioned in 2 slides, there are some more slides, or you can go through them later by yourself. I don't want to go to them. Uh, so already I explained them. These 6 steps are I just covered them 2 slides, but in fact, if you want to really learn each step, again, I have put already some PhD thesis on Moodle, but there are a lot of references you can go and study on your own and realize how you can uh, apply these steps in your process heat integration. However, I want to emphasize that for your project that you are going to present, I expect that you consider this kind of approach of process heat integration. Okay, so don't forget that when you present your project, you must present that you consider process energy efficiency. You know, uh, and again, I want to emphasize that process energy efficiency is uh, a function also of optimum water consumption in the process and the steam consumption of the process. I mean, in other words, utility. You need to consider the utility in the process as well. We cannot just say I use I use a heater to increase the temperature. Okay, use a heater. What is that heater? Is the heater uh, uh, does the heater use steam? Okay, if you steam, what is steam? Low pressure steam, high pressure steam, medium pressure steam, or maybe the boiler doesn't use the steam. The boiler just uses electricity, electrical heater. You know, you need to consider that. So if you use electrical heater, so you need electricity. How that electricity is generated? You need to think about electricity. Okay, of course, I don't expect you to be to show me a very full design of utility, but you have to present that you consider something at least at the level of this class that so that you can justify your process is energy efficient. Okay, so now I want to talk about something very interesting in terms of increasing the energy efficiency of any process, in fact, and it is called heat pump. In French, we say pompe à chaleur à absorption. In fact, this is the absorption heat pump, but in general, heat pumps um, are uh, in different shapes and designs. Absorption heat pump is just one way of heat pumps. I just before I go to heat pumps, I raised a question for you, and I want you to answer this question next week, or maybe it will be in your exam. What is the difference between a heat pump and a refrigeration system? Now you are going to understand why they could be similar or they could be different. Just typically, if you look at this picture on the left hand side, typically, let me tell a heat pump is a kind of device, is a kind of equipment, where you take some heat at a low temperature, okay. You take that heat by a special uh, kind of refrigerant, by a special medium, a special liquid, okay. Uh, you take that heat at low temperature by the refrigerant, and the refrigerant is is going to be uh, pressurized at a specific step. We call it pressure rising step. Okay, for example, by a compressor. Okay, in this step, some energy is taken, and then that fluid, that working fluid, refrigerant, whatever you call it, it's better to call it, in my opinion, working fluid, because refrigerant, when you say, people think that it is a refrigeration system. Let's say working fluid. So that working fluid, after it is pressurized, okay, goes to a condenser and becomes condensed. As a result, some heat is going to be, released like QC to the atmosphere or to the target location. As a result, temperature drops, and then the working fluid passes through a kind of a sort of pressure lowering device (PLD), which could be, for example, an expansion valve, and then it's back to evaporator. So the working fluid, as you can see, travel the cycle between an evaporator and a condenser. Okay, and as you see, takes some energy at low temperature, and then in a pressure rising device, uh, it is pressurized. Okay, and also after pressurized, temperature also increases. It goes to a condenser, releases energy, and then come back to PLD, pressure lowering device, depressurize, back to evaporator. This is a kind of regular heat pump that even if some of you you have houses, you have you have, I'm sure you have seen them.
Doctor, I'm sorry, I have a question.
Yeah,
I'm sorry.
sure.
When you talk about an expansion valve,
Yeah,
it comes to my mind the Joule Thomson
it can,
effect.
yeah,
Is
it
that what
could,
you mean?
yeah, it could
Okay.
be, yeah, it could be like that. It could be a kind of passing through a capillary. There are different ways of the of. That's why in general we say pressure lowering device. It could be a throttle valve. It could be other designs. But what is absorption heat pump? It's the same concept, but absorption heat pump here is based on kind absorption of the working fluid and then its desorption, and you are going to understand very soon what it means. So imagine, let's assume that we have a working fluid, for example, ammonium mixed with water or water mixed with lithium bromide. Usually in heat absorptions, we have this kind of binary fluid, working fluids, so that one of the ingredients is more volatile than the other one. For example, in the case of ammonium and water, so ammonium is more volatile than water. Okay, so so one fluid is more volatile and the other fluid is called solvent here. So what happens is that let's start from evaporator. Okay, in evaporator, the volatile component of the working fluid, okay, here takes the energy at low temperature, the energy QE, takes the energy QE, and that is transferred to a kind of absorber. In absorber, the volatile part of the working fluid is absorbed in the solvent. Let's say ammonium is absorbed in water. This absorption is exothermic. So some energy like QA is released. Okay, and after that, after absorption, the two now we call it here, we call it now weak solution. After ammonium, for example, is absorbed in water, then this solution we call it weak solution. This weak solution is pumped. For now, forget about this SHX step. I will tell you later what it is. Working fluid then is pumped to a generator. In the generator, what happens is that by giving some energy like Qg, the volatile part of the mixture is dissolved, is separated from the solvent. Okay, is dissolved. Okay, but it takes energy. Okay, so uh, at, at the generator stage, when it is dissolved, the temperature increases because of because of the Qg. So the solution, the solvent is gets separated from the volatile part. Solvent is going to be sent back to absorber tank or absorber whatever container, but the volatile part is going to be sent to condenser. In the condenser, since that working fluid here has high energy and high pressure, inside the condenser loses some energy like QC. Okay, By losing the energy, temperature drops. After that, that kind of uh, cooled working fluid passes through a pressure lowering device like expansion valve, throttle valve, whatever you can use, depends on the design. The pressure also drops. The pressure drops and it goes back to evaporator. And again, and after that, again the evaporator, the volatile working fluid takes the energy from QE. It goes to absorber. In absorber already solvent is there. Again, uh, you have absorption, you lose energy. You pump it. So due to pumping, you pressurize the working fluid. It goes to generator, gets energy, and then dissolve. It's very important here in generator dissolption of the volatile part from solvent occurs. The volatile part goes to condenser. So this is the loop where the volatile part rotates in order to eventually get the energy of QE and release energy at high temperature like QC. But what is this heat exchanger? This solution heat exchanger is just, it's just one step that you can put so that uh, some of the heat from the solvent can be exchanged to, can be exchanged with the solution here, so that the QG that you need to use is going to be less. In order to minimize the QG, you can put a heat exchanger so that you get advantage of the hot or maybe warm, I can say warm solvent. That's it. So the coefficient of performance of the heat pump is calculated by this equation, QC plus QA divided by QG. So QC is the energy that you release uh, in condenser at high temperature. QA is energy that you release um, uh, during absorption of the volatile working fluid in the solvent. And QG is the energy that you use in the generator in order to dissolve the volatile part. Okay? But this diagram is very interesting, very important diagram. This is just one example that shows how pressure and temperature look like. Let's start from the E, evaporator. So you see here temperature, for example, could be 30 Celsius, okay, just as an example. So here the volatile part goes to absorption. In the absorption, see pressure is the same. So evaporator and absorption, they operate at the same pressure. Okay. So after absorption, you have pump. So you are pressurizing the binary working fluid to the generator. Inside the generator, you have high pressure. Okay. Also high temperature. Why? Because you input energy in the generator. So that's why you can see that temperature in the if you just follow evaporator, absorber, and generator, you can see that temperature of absorber is higher than temperature of evaporator, and also temperature in generator is higher than temperature in absorber. Okay. But okay, so here at generator, as we discussed, we have desorption. So the working fluid, the volatile part, goes to condenser. So of course temperature drops because energy is released, and solvent is back to absorber. Okay, and we can have a heat exchange with the pump fluid. And you can, and it's very important to pay attention that temperature of condenser and temperature of absorption are similar. See, but pressure in condenser is higher than pressure in absorber. So if you want to know more information about heat pumps, you can go to this reference. It is an article. Uh, Inside that article, there are some more references in order to understand how heat pumps work. So anyway, the idea in general is that you take energy at low temperature, okay, like inside evaporator, and eventually you release energy at a high temperature in condenser. Okay. Okay. Now, how you can integrate a heat pump to a heat exchanger network? This is something interesting. If you remember, we said previously that uh, when you design heat exchanger network, uh, so by pinch design method or by pinch analysis method, you should never cross energy from the pinch point. You know what I mean? You can never consider a heat exchanger that, uh, for example, if you can never a heat exchanger that crosses the pinch point. So that hot stream above the pinch uh, exchange energy with cold streams below the pinch point. You can never do that. Okay, so no. But there's one exception for heat pumps. You can design a heat pump in your heat exchanger network regardless of the pinch point. You can do that. If you want to know more, again, go to this reference. You can have all the discussions. So how we can have a heat pump, absorption heat pump, AHP, around uh, heat exchanger network. So what you can do is that you can assume that uh, you can have uh, some energy. You can take some energy from the hot streams below the pinch point. Okay, you can get some energy from some warm streams. For example, those streams that are not really hot, as you see, for example, here maybe the temperature here is like let's say 60 Celsius. For example, you can take some energy from warm streams below the pinch point. Okay, and then some within the heat pump, by using the heat pump, you you exchange heat to some cold streams above the pinch point. So in total, you can have QC and QA, those energies to to warm or to heat up some of the cold streams which are above the pinch point. Okay, but if you remember, uh, in the generator usually any temperature is higher than temperature of condenser, absorber, and evaporator. So if you want to have the energy required for the generator of the heat pump, we can take some of the energy, some of the enthalpy, whatever you call it, from some warm streams above the pinch point, okay, in order to supply the energy for the generator. So as you see at the end, by using this heat pump, okay, so um, you are minimizing minimum heat recovery and minimum cooling recovery of the system. Why? Because let's say without heat, without heat pump, if you just do a regular pinch analysis, let's say for example, the uh, this is as it is shown. This is the uh, en- uh, energy that you need from utility to heat up these cold streams here zone. But since you use this amount of energy, okay, I mean you supply this amount of energy from the heat pump, so the energy that you need is then MHR minus QC and A. And in other words, the energy that you need from utility is now less just by using the heat pump. And also from another point of view, since some of the uh, hot streams uh, were cooled by QE here, okay? So the cooling water, for example, that you need in the uh, from the utility is going to be less because already you heated up some of the streams by evaporator of the heat pump. Okay, so this is the way that you can apply a heat pump. You can integrate the heat pump to a heat exchanger network to even lower your required energy uh, even to some more extent. This is the way that you can do a very good energy efficient. But of course, what we are discussing today is just to give you this flexibility that exists. It is a matter of some um, not really sophisticated kind of systematic energy analysis, development of your tools, simulation and the calculations and everything. But it is a very, very interesting topic in heat integration of the process. By the way, the only thing is that there are some remarks here. Heat pump is very interesting equipment because you take energy from a low temperature, as you saw here. You take energy from low temperature, okay, and you lose energy at higher temperature. For example, here temperature is 120. Okay, it's very interesting thing, but you have to be careful. In terms of operation cost, is not very expensive, okay. But in terms of investment, capital cost, heat pumps could be expensive. So, if you remember in the when we discussed six steps of process heat integration, the sixth part was to apply technical analysis. You have to do technical analysis and to find out if considering a heat pump into heat exchanger for worth it or not. Okay. Um, that it's really related to the economy of the process. But something else that I want to pay attention is the working fluid in heat exchange. So the working fluid should be something environmentally pleasant. Do you remember what kind of refrigerants are used in refrigerators? Anybody can say what kind of working fluid is used in the fridge at home, at your home? You know that you have a refrigeration system at the back. What is that working fluid that passes through the refrigeration system?
I think the
CFC.
R134. I'm not sure.
Yeah, what is the name? What is the molecule?
Something about with chlor, but I don't remember. I'm sorry.
Period.
Ferrions.
CFC.
Yeah, ferrions, right? But they are absolutely bad for environment. You know that that's the issue with the for working fluid in the fridge. But fridge are a small devices compared to a large factory. So if you want to design a biorefinery with a very energy efficient system, you have to be careful. You cannot use toxic things. It has to be environmentally acceptable. That's very important. That's why so far, for example, people consider ammonium and water or water in lithium bromide. So this is a kind of procedure how you can integrate absorption heat pump to process. Already I discussed. You can go through and you can go through this reference and get more information. Already I discussed this diagram. So this is an example that was applied by a PhD student a few years ago for a furfura plant, a furfura biorefinery plant. So you know that in furfura plant, at some stage, at kind of final stage of the process, you have a distillation column. So in distillation column, you know that at the top you have a hot stream. So this hot stream is a source of energy. Okay. So this student considered the energy around the condenser, the energy that can be released from the condenser, as the source of evaporator in a heat pump. So he designed this kind of heat pump so that the energy that is captured by a condenser, okay, can be the energy that is taken, for example, at this temperature at 87 Celsius, can be released at 80 Celsius. Okay, can be released at 80 Celsius. Can be used for that energy. Then can be used for other parts of the process. His estimations showed that if we don't have any heat exchanger network, any heat pump, whatever, the total energy that you require for heating and the energy and then the I mean the power that you need for heating and the power that you need for cooling are going to be 14 and almost 26 megawatt, okay, respectively. But if you apply heat exchanger network, for example, by a pinch, uh, the required heating is going to be decreased to 11 and the required cooling is going to be decreased by 23.4 megawatt. But if you apply heat pump, then you get more uh, promising energy saving. So if you apply heat pump to this heat exchanger network, the required power is going to be 7.4 and the required power for cooling is going to be almost 20 megawatt. So in overall, with respect to the base case, uh, the total power that you need to supply energy, to supply the heating, is is going to be decreased by 48%, and the power you require for cooling is going to be decreased by 23%. That's huge, it's a lot. It's not really a joke. 48%, 23% is really a lot. So you know that energy is, especially somewhere in Canada, is very expensive because of the climate of Canada. Anyway, energy is expensive. So that's why um, you know that when you do a techno economy analysis in the process, you have capex and you have opex. You have capital expenditures, operation expenditures. So capex is about equipment, but operational uh, expenditures are related to mainly chemicals that you have to use and utilities. And the most important utility is about energy. How much energy you need to system. If you minimize your energy, then you are good to go. You are at a very good point. This is another. So this is another kind of overall schematic of um, energy saving, especially once you integrate a biorefinery to another existing factory, for example, pulp and paper. It means if you do a very good process heat integration, okay, if you could do a very good process integration, as you saw here, the total energy, for example, for this fluoropollen, the total energy that you require for heating is going to be to down to, from 14 is going to be down to 7.4 megawatt. Okay, so in other words, the energy that you are going to be the energy that you are going to borrow from another factory is going to be less. So dependency of the biorefinery to the factory, like a pulp and paper, for example, pulp and paper mill is going to be less. It's going to be 7.4 megawatt only. Okay, so the kind of complexity in the integration between two companies, two factories is going to be also less. That's the schematic that is presented in this diagram. This is another example. This is the process for ethanol biorefinery. As if you remember in previous weeks, we presented that how ethanol can be produced through fermentation from biomass. Okay, if you remember. So same analysis has been applied to this process. Again, by applying heat exchanger network and analysis and absorption heat pump, the total energy required for heating and total power, the total power required for heating and the total power for cooling decreased respectively to 60% and 25%. That's a lot. But I want you to pay attention to this process flow sheet. So again, I just want to remind you that uh, if you want to do a process heat integration, the first step is to do process flow sheet. Process flow sheet and then process simulation. So you need to consider process flow sheet, apply process simulation, then you have to do benchmarking. You have to compare operation of your process to simulation data, or compare your simulation data and your plant data with other plants somewhere else to identify the strength and weakness of your process, especially heat sink and heat source, water sink and water source of the plant. Okay, and then but as you see in this diagram, for example, we have identified heat sink and heat source at different zones of this process flow sheet. By identification of that, you can, develop your thermal pinch analysis and identify um, how you can, uh, determine how you can apply a significant energy saving in the process. So if you want more information, next week the TD that you have is about pinch analysis. It's a practice that you are going to um, carry out to just put your hand on. But I strongly suggest that you go and study references that exist in the Moodle and other references around public literature to really familiarize yourself with energy saving, because people who have a robust knowledge in energy saving in any process, they will be at a good position at their workplace, even as an expert. It's very important thing, because energy is an important thing. And in biorefinery in general, since we are uh, dealing with a lot of uh, uh, chemical reactors and different and streams with different temperatures. So designing um, an energy efficient process is the key. Okay, you cannot just say, okay, I will go to lab. I add a reagent to my biomass. I get a new product. Okay, bingo. Let me scale up and commercialize my work. I'm going to be rich. No, if you want to be rich, you can be, but you have to consider that your process has to be optimized so that the operation cost of the process is minimum, or I can say optimum. So this is the part for energy saving. I hope you enjoyed this part of the course, even though it's quite compact. Um, I did my best to slowly explain these important aspects in process heat integration. So let's have just 2-3 minutes break, not more than that, because I want to go to next part of the course. We can be back at 2 o'clock, and then I will talk about the next chapter of the course. But if you have questions, just ask me.
So I have a question, a short question.
Sure.
Uh, I think that if I remember, we can also break the pinch point with heat engine and combustion chamber.
I don't hear you well. Can you talk louder?
Uh, do you hear me now?
Yes.
If I remember, we can cross the pinch point with the heat engine and the combustion chamber also, like a heat pump.
Yeah,
It's not
yeah,
just heat pump.
yeah. There are some exceptions that these are more advanced heat. Myself, I did my master's project. My master's thesis was on pinch analysis of heat exchangers, but it still was the basic. Heat pinch analysis has a lot of advanced topics. Uh, so you're right. There are a lot of things around, but for now, let's stick to what we discussed today.
Yeah, and if I could remember, sometimes you can break the pinch. For example, sometimes we want to modify a process, available process. We have some bottlenecks, and we can cross the pinch point to,
Yeah,
insert a heat exchanger,
yeah.
new heat exchanger.
But the key point is uh, the, there should be something very clear. The key point is, uh, for example, when we talk about uh, uh, pinch point, our focus is on process-to-process heat exchangers. Heat pump is not a process-to-process heat exchanger. That's why we say we can violate it.
Yeah.
So this is the key. Whatever. That's why some exceptions come in, but the confusion should be solved now. You are saying that between process-to-process heat exchangers, um, you cannot have violation of the pinch point. Because, for example, when you talk about combustion, combustion is a utility. Okay, it's not process to process. So these are the things that we have to be clear.
Yeah,
But
thank you.
pinch, uh, but regarding the pinch itself, just I want to emphasize again that uh, the concept of pinch started from thermal pinch analysis. But now we have pinch analysis not only for water optimization consumption, also for example hydrogen. Like for example in any let's say in a gasification process that you are producing hydrogen. At some parts maybe you have to use hydrogen. Imagine that you have gasification process that is integrated with the Fischer-Tropsch process. So you have somewhere demand of any hydrogen and somewhere you have the supply of hydrogen. Again, you have hydrogen pinch. This is another concept that exists in energy industries. So I really strongly recommend to you guys that try to learn pinch. It's a very interesting tool. And I know that there are a lot of job markets for people who are good in energy systems.
Also, process design by Robin Smith is a good reference for learning pinch.
Exactly. The core. Actually, I forgot to put it in. I thought it is in Moodle
I
already.
can send it to you if you want.
I have it, but I thought it's already in the Moodle. It's not in the Moodle?
I didn't find it in the model.
Okay. Just send me a reminder. I'll put it. Yeah, the book by, because Pinch started in Manchester at the UMIS. I think UMIS
UMS University.
now is called just Manchester University, by a Professor Linhof, if I'm not mistaken.
Yeah,
Uh,
exactly.
and it's a very interesting topic. Yeah, but there is a very good process design book uh, from, I forgot what is this professor's name. Charles, the one, the author of
Robin Smith.
Robin
Robin
Smith.
Smith.
Yes, Robin Smith. Yes, Robin Smith has published a very good process design book on pinch analysis. But you know, he has started, but now there are some more books on pinch analysis. You don't need to just read that one. By the way, now let's put our focus a bit more fun. Okay, pinch analysis is more quantitative work and about it, which is very very interesting. But now is this chapter 10 is a bit more fun in terms of, I mean, understanding. Okay, at the end, why biorefinery? Why biomass conversion? What can we do with biomass? Why we have to do biomass conversion? We have been talking about, yes, with biomass is a renewable energy resource. We can produce biofuel. We can produce bio-based materials. Okay, let's elaborate a bit more. Let's have some more insights in some material that we can produce with more value added properties. That's why today we are going to talk about value added products from biomass, or produits à valeur ajoutée issus de la biomasse. So let's for now put our focus on uh, chemical industry in general. You know that chemical engineers, are supposed to be one of the one of the richest engineers, right? Because of the chemical industry. Chemical industry globally has a turnover around $5 billion. Okay, sorry, $5,000 billion. Huge, it's big. And if you consider some countries, you can see that some countries they are really really benefiting from selling chemicals, like China, United States, Japan, Germany, France, Brazil. Uh, Canada is unfortunately not as good as China and United States, but it can be, Canada can be a big player too. Why? Because Canada is has a lot of natural resources. But back to our topic, which is about biomass conversion. If Canada, uh, makes enough strategies, um, it can be also a big player in production of chemicals. But in Canada, there are not some parameters that impact its chemical industry. For example, uh, market, the price of the petroleum, and some other factors that are listed here. But definitely Canada can be a big player in chemical industry. But still, 31 billion dollars is not low. $31 billion only chemical industry. You can consider the total, um, uh, let's say, um, what's called the GOP in Canada. I don't recall what is that number, but this I think 31 is a big portion of that number. I think it's like maybe 25%. Maybe one of you can correct me. It's a big, big compared to other industries like informatics, IT, electronics, agriculture, blah, 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 $31 billion is really significant. So let's go to next step. Here we have a kind of classification of some special markets. Markets of commodity chemicals, special chemicals, fine chemicals, and polymers. Okay, this is the global market for some of them in 2005. Okay, and you can see that, for example, in terms of commodity, those specials or fine chemicals. Fine chemicals here means, for example, pharmaceuticals, medicine, even beauty products like cosmetics, whatever. That they require very, very high purities. You can see that um, these are big markets, but bio-based products, they have in total very low uh, contribution in this market. It's less than 2%. But it is expected that by 2025, okay, the market penetration of these uh, bio-based products in this market is going to be more, from 6% to 50%. So what is market penetration? Means um, the total volume of the selling of a product versus uh, uh, the total target of that market. Means that so that's why this is called market penetration, in French, taux de pénétration. If this is it's a kind of business indicator of any product. So as you see, it is in another point of view. Uh, uh, by 2025, it is expected that bioresource or bio-based products compared to similar products that are produced from petrochemical industry is gonna is gonna be like with the ratio of 1:3. Or in other words, uh, almost 25% of the chemical products are going to be bio-based. Okay, that's something. It's significant, really significant. By 2025, it is, but this is the kind of anticipation. But maybe it never happened. It's going to be less or maybe higher, depending on the market fluctuations and restrictions that are are there. In terms of different markets of chemical products. You can see that uh, it is anticipated by 2025, 320 mega dollar or giga dollar, whatever you use, are going to be attributed to special chemicals, okay, and 100 mega dollar or $1 million uh, by commodity products, and less for example, fine chemicals. This is the kind of market, the kind of distribution of the market that exists. But something that we need to consider is how uh, we can transfer from petrochemical based chemicals to bio-based chemicals. When we say petrochemical based chemical, means chemicals that they have original source in crude oil. It's a fossil fuel. But bio-based, we are talking about, for example, biomass. So there are different factors that impact this kind of transition. Uh, and this transition can be a sustainable transition because we are talking about biomass, which is a renewable energy source. But if we make sure that in terms of environment, in terms of economy, all these processes that we've developed are going to be promising, that process can be a sustainable bio-based process, sustainable biorefinery or a biochemical, bio-based chemical. Okay, but beside economy and environment, another parameter that is important is about it's just politics about the strategy. You know, countries compete together. Just assume now that we are in pandemic era. You remember that a couple of months ago there was a big competition to make COVID-19 vaccination, and Russia was the first country that announced that okay, I made the corona vaccine. You know, countries they want some countries they want to be always the first. So uh, all these kind of politics impact uh, the uh, the growth and the rate of transition from, for example, petrochemical based chemicals to bio-based chemicals. So that these are the parameters that impact. Okay, so that's something that we need to consider as a general how we can make this transition. But now let's talk about a bit some challenges that involve for that kind of transition. You know, there is some advantages and disadvantages if you want to produce one chemical, one product, let's say a kind of pharmaceutical, a kind of medicine. You want to make a special medicine from, let's say, a biomass. Okay, but that medicine could be also produced from a chemical that is backrooted to petroleum, crude oil. So there are advantages and disadvantages. One advantage is that, for example, biomass, as you know, is full of oxygenated molecules. You know, for example, it is made of aldehydes, ketones, or organic acids, alcohol. All of them they have oxygen. But you know that making oxygenating of regular organic molecule is expensive. Is a challenge. As shown by here, if you want to oxygenate a kind of, let's say, aliphatic molecule, you have to spend a catalyst, you have to go to high temperature to make it oxygenated. But biomass already has oxygen, so that can be advantage. On the other hand, due to structure of biomass, in general, the path that you have to take to reach that final medicine, that is our example from biomass, can be completely different from the path that you used to take from a petrochemical based material. Okay, so the challenge here is okay, you have one biomass, you you have a target to produce a specific product, but from biomass. So the advantage is you have, for example, if your final product should have oxygen in the structure, you have already oxygenated molecule. But due to different structure of biomass, for example, cellulose compounds, I mean, glucose, hemicellulose compounds, lignin compounds. You have a kind of more a kind of a specific structure, and therefore uh, transforming that molecule to the final product requires a different pathway, as shown in this diagram. Okay, for example, for biomass, you have to do kind of dehydrogenation, for example. So there are different paths, but it's not the only thing. There are different things that you may face during biomass conversion. In other words, what if I want to summarize is uh, you can produce a similar product uh, from biomass, okay, but there are advantages and disadvantages. The big disadvantage is is a new path, and that path can be completely different than the process based on a regular petrochemical based process. So you have to do a lot of research and development. You have to think about all those talks that we have had so far: energy efficiency, um, environmentally friendly, and technical analysis, and many more. But it is at least uh, one advantage that biomass already is an oxygenated molecule. So by this advantage, you may end up sometimes with a process that even is less complex than a petrochemical based process. So from another point of view, let's think about the kind of um, uh, uh, policy in um, that should be made to make value-added products from biomass. We should not be blind-minded just to go and produce, for example, pulp and paper products. Maybe from a market point of view, if we are smart, we can produce specific chemicals so that we make a lot of money. We make and we contribute to uh, wealth of the society, country, even the world. If you look at these two diagrams, which is for example, a diagram for a petrochemical industry, you can see that um, on the pie shape on the left, we are comparing final utilization of the uh, petroleum products, okay, for fuels, for chemicals, plastics, and rubber, and other kind of fuels and products. You can see that uh, uh, total consumption of those petroleum products for making chemicals, plastics, and rubbers is just 4% of the overall consumption of those petroleum-based products. Just 4%. But in terms of profits, in terms of money, that 4% is associated to 42% of the total benefits. Okay, that's a big advantage. But now let's look at, for example, a forestry in the industry. In forestry industry, okay, the main products are wood products, pulp and paper, and other fuels and products. Okay, so similar to the one here, and you can see that uh, regardless of the contribution of the total consumption and total profit of each of these products, you can see that um, there is no discussion on uh, chemicals, plastics, rubbers, and whatever, and other value-added products. In other words, we have to learn. We have to learn from oil and gas industry how to make money, how to be smart in making money. Yes, you can make a lot of fortune by producing wood products, by producing pulp and paper, and producing fuel. Okay, but if you want to be richer, uh, put the focus on making special chemicals, plastic or plastic chemicals, polymers, some other uh, chemicals that uh, make you be richer, will help you make more money. Okay, that's the message that uh, uh, I can say biorefineries should learn from oil and gas industry. So in other words, they are not two different worlds. They are, each each section should learn from the other one. So there should be back and forth exchange of information. So you see what are the opportunities there, how another world is rich, and I take those patterns in my industry, and then I make more money. So that's the attitude that in biorefinery we have to consider. If you This diagram is very interesting, and it is more discussed in this report by FP Innovations. I want you to go and read that report. If you consider this diagram, by the way, what is this diagram? This diagram considers uh, market size, okay, market size of different products from biomass, and value, price, or value of the product. As you can see, for example, the market size of cellulosic fibers, like for example papers, is is big. It's like almost 2 million per year. Okay, 2 million per year. Okay, or can say yeah, 2 million per year, 10 power to 11, almost. Okay, but the price of cellulosic material is less than $1 per kilogram. Less than $1 per kilogram, even though the market is high. But if you follow this trend, if you produce special chemicals, for example, taxons are a special medicine, for example, for uh, painkillers and whatever. If you change your attitude and make special chemicals, for example, special pharmaceuticals, okay, your market size is going to be smaller, of course, because um wood, for example, can be used for everybody, but medicine is used by people who are sick, so market size is smaller. And on the other hand, making pharmaceuticals, you need to be very careful. You cannot have contaminations in the pharmaceutical products, so process is more delicate. And on the other hand, the value of the product that you make is much, much more. If, for example, taxons, maybe the market is smaller. Okay. For example, if the market in the y-axis based on kilogram could be, for example, 100 kilogram that you make per year, relatively, but the value is like $1 million per kilogram. It's different. So the attitude in making a biorefinery should be in this way, that if you want to be rich, you need to consider a kind of market size and value of the product and make a decision uh, which product makes more sense for you or for your company to put investment. So this is a graph that shows a typical example of some final products that you can make from biomass. Imagine that, for example, you have a forestry biomass, like a woody biomass. This is my pen. So this is the start from here, on the left. Let's say you make uh, primary products from biomass, like furfural, acid succinic, and acid levulinic. Okay, you make primary products, just three primary products from a biomass. From that three primary, you can make secondary products, different products. Okay, and by those secondary products that you make from the primary ones, you make some intermediate products. Intermediate means you make products that are not final products yet. You may use them, but usually the end users that are regular people in society, they don't use them. These are the usually fits for final products. So in intermediate, you make a lot of aromatics, resins, solvents, and many more products. And by a combination of these intermediates, make a lot of final products for different sectors. For example, food industry, for chemical industry, environment, domestics, textiles, transportation, communication, health, and many more. You know, so this is one way that you can make a lot of money. This is just an example. So let's now for today only consider one specific example to make one bio-based product, which is xylitol. Xylitol is we will see, is a chemical that has food applications, even pharmaceutical and medical applications. So it's a very interesting chemical. But xylitol can be produced direct from xylene, okay? Uh, Xylene of biomass, you know. So talking about biomass, you can apply hydrolysis and make xylose from biomass, and then by hydrogenation, you can make xylitol from xylose. It is just a chemical reaction, but there are some issues in there. First of all, imagine that you want to go through this process. So after you do hydrolysis, you have to do some other purification steps like detoxification, biotransformation, and then you should have separation purification until you have the xylitol. Okay, so even though by looking at this simple chemical reaction, it looks like, oh, that's easy. Let's just produce xylitol from xylene as a biomass. But there are some steps that you have to consider. All those um, separations and purifications until you get the standard grade of the final product. Why? Because there are competitors. For example, somebody in oil and gas industry can just use a conventional xylose that is produced from uh, petrochemical industry, okay, and just and just do hydrogenation and get the and that's it. They don't have to worry about detoxification and biotransformation. This is the extra step that you have for biomass pathway. So the regular pathway doesn't have those steps. Okay. So this is one thing that sometimes you need when you want to develop a process from biomass. You have a competitor for example, in oil and gas. You need to make sure that your process is uh, is computing to the process that already exists. By the way, it is really possible to make xylitol from xylene, and usually the grade, I mean the efficiency is 50. I mean the yield is 50% to 60%. So that's really interesting. By the way, this is just one example to make xylitol. Another example is Fischer-Tropsch. I think you remember last time that we said uh, Fischer-Tropsch is the process where syngas, carbon monoxide, and hydrogen are used to make synthetic fuels. So Fischer-Tropsch is the process that was developed by Germany during the Second World War to make fuels. If you remember last week, I think about 2 weeks ago, we said that one of the products from Fischer-Tropsch is diesel. Okay, is diesel. But you can make also biodiesel from biomass. And to make biodiesel from biomass, you have two options. Either you use uh, agricultural crops like oil seeds, which is not uh, ethically is not a good way because they are food. But you can use secondary or even tertiary generation of biorefineries, and then do gasification, make syngas, and then and make diesel. That is called then biodiesel. You know, so this is the way that. Sorry, it's not biodiesel. I mean, I have to correct my words. When because biodiesel is through trans certification that is applied to oil seeds, but if you use gasification and then make CO and hydrogen and then make uh, diesel is not the trans certification process. But if you use microalgae, you can use microalgae and make biodiesel because microalgae has significant oily parts. Okay, so I have to correct my words. By the way, by one of the important products that you can make, for example, from biomass is really hydrocarbons. So by having syngas, carbon and hydrogen, you can make biocarbons. It could be methane, it could be gasoline, diesel, whatever. You can have, depending on the reactor design and the operating condition, make them, and then you apply distillation columns, and then you get different cuts to obtain desired products. Okay, so this is about Fischer-Tropsch. There are many more products that you can make from biomass. Uh, on Tuesday, maybe I will cover a little bit mostly about the lignin, because lignin is a very interesting part of biomass. But the rest of the chapter is just really easy. You can follow on your own, just to familiarize yourself with different products and their markets that you can get from biomass. Okay, I think it's enough for today. So if you have any question, just ask me.